Hello and welcome to another episode of Twimmle Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Once again, thanks to everyone who sent in their favorite quote from a recent podcast. Another batch of stickers got mailed out this week, and please keep those quotes coming. We've had a blast getting your perspective from each talk. If you're new to the Twimmle family, you too can get a sticker. Just send us a comment via the show notes page, tweet us at TwimmleAI or at Sam Charrington, or share your quote via a post on our Facebook page. Before we jump into today's show, which I'm sure you're going to enjoy, I'd like to take a moment to remind you all about my upcoming event, the Future of Data Summit, which will be held May 15th and 16th in Las Vegas, Nevada. I'm really looking forward to the summit, and I hope you can join me there. You'll hear from industry leaders and technology users on how they're taking advantage of emerging data-centric technologies like IoT, blockchain, deep learning, and more. You'll learn a ton. I'm continuing to add new speakers to the lineup, including Jennifer Prenke from Walmart Labs, who will be joining us to talk about what she calls data mixology. Jennifer currently leads a team of data scientists and engineers working on improving the online experience of the Walmart customer by integrating Walmart stores data with e-commerce data. She also manages the metrics and measurements team there, a group in charge of creating metrics to measure the impact of all new features and algorithms, as well as solutions to automatically control and manage all machine learning algorithms in production. She'll be talking about the importance of finding and fusing data to making machine learning predictions in production and describing the evolving platform that Walmart's put in place to facilitate all this. Jennifer is just one of a whole lineup of great speakers I've got for the summit, and the summit is just the first 2 days of the Interop ITX conference, which offers a week full of great educational content for folks interested in data and analytics. In addition to a dedicated data and analytics track at the conference, there will also be an AI theater and demo showcase dedicated to the practical application of AI, deep learning, and machine learning for traditional enterprise tasks such as dynamic pricing and insurance, perfecting the retail customer experience, optimizing job costing, transportation expenses, and more. Case studies will be presented by businesses employing successful AI strategies and will provide strategic guidance and suggestions for attendees to utilize in their respective businesses. Accompanying the AI Theater is the Demo Showcase, which will provide a hands-on lab demonstrating real-world AI technologies. If you have any questions at all about the summit, don't hesitate to reach out to me. And to learn more, visit TwimmleAI.com/futureofdata. The code I provide on that page, which is simply my last name, Charrington, provides Twimmle listeners with a 20% discount when they register for Interop ITX. And now about today's show. My guest this week is Scott Stephenson. Scott is co-founder and CEO of DeepGraham, which has developed an AI-based platform for indexing and searching audio and video. Scott and I cover a ton of interesting topics in this talk, including applying machine learning techniques to particle physics, his time in a lab 2 miles below the surface of the Earth, applying neural networks and deep learning to audio, and the Deep Learning Framework Kur that his company is open sourced. I know you're going to love this one. And now, on to the show. Hey everyone, this is Sam Charrington, and welcome to another episode of This Week in Machine Learning and AI. This week, I've got Scott Stephenson on the line with me. Scott is co-founder and CEO of machine learning and AI startup DeepGraham. Scott, say hi.
Hi, thanks for having me, Sam.
It's great to have you on the show. I think the best place to get started is to maybe have you spend a little bit of time talking about your background, because you come out of physics, right? Not audio, speech, and all that?
Yeah, absolutely. We are, DeepGraham is an audio AI company, but our background, or most of the technical people in DeepGraham, our background is in particle physics, or at least some form of, deep physics. And for me and my co-founder, Noah Shetty, we both were doing particle physics before we started DeepGraham, which was searching for dark matter. And this is about you build an experiment that sits around miles underground, essentially, like 1 mile, 2 miles underground. The deepest labs in the world are 2 miles underground. And our experiment was in the deepest lab in the world in Western China. It was called Panda X. And we built this experiment over the course of 4 years with a lot of other people, with around 24 other people, and with the help of the Chinese government. And that's an interesting story. But yeah, and the techniques that we learned in building this experiment, we figured out were like really applicable to audio. And the reason is that physics is very at least particle physics at the very hairy edge of research is still analog, and you still you still look for particles using analog detectors. They're called photomultiplier tubes, and the signals that you get out of these are just a waveform. It looks a lot like an audio waveform, but it's at a much higher sampling frequency, and those waves that are contained in the output of these photomultiplier tubes, the signals that are in there tell you the signature of the particle that you're seeing. So you might see a single photon, you might see a big splash of a muon in your detector, but it's all contained in those waves. And so what you have to do is extract that information from the photomultiplier tubes and then make a guess, did you see dark matter or not? And so we got very good at doing that. And it's actually really interesting because the state of the art in particle physics is essentially a lot of humans sitting down, figuring out how do you extract information from these signals. And, maybe you've heard of like the Higgs boson being discovered a few years ago. A lot of people, yeah. And that was done by thousands of scientists sitting down and saying, hey, I really want to find the Higgs boson. How do I make cuts in my data? How do I process my data to figure out, or to make my signal to noise, good enough to find these particles?
Right.
And this is actually a lot of this hard manual labor of figuring out these cuts is done by machine learning now. So people will build boosted decision trees, or that's not necessarily the realm for neural networks, but boosted decision trees and other statistical machine learning techniques, people are figuring out how to sort of automate this. But that's like the world that we came from, essentially, and we were on that. We were in that area thinking like, man, this sucks. Let's automate this. How do we automate it? And because I feel like a machine already, just going through, like, here's another plot. Did this work well? Did that not work well? Like, what went on? And it's like, this could all be done with a machine. And so a lot of the people that are in DeepGraham now, we were all sitting at University of Michigan thinking, how can we make machine learning or how can we jam machine learning into physics, particle physics, and then like extract something out of it?
And how far did you get down that path? Did you actually complete the jamming, or did you end up leaving and going off to start DeepGraham before you fully applied ML to the particle physics?
Yeah, so it's varied for the different people in DeepGraham. So I did finish my PhD. I finished about 2 years ago. And Noah, who is my co-founder, went to a PhD program at Stanford, like actually didn't even start it. He came out to the Bay Area, and we were working on DeepGraham at the time, and we got a little bit of funding, and he was like, you know what, let's not do this physics thing. Anyway, but a couple other people in DeepGraham either finished their PhD or, got a master's and left after that. But we were definitely successful in sticking machine learning into a particle physics analysis pipeline. And in particular, for dark matter, what we did is reconstruct events in a 3D position. Reconstruct the 3D position of the events that are happening inside. So the way that this works, I mean, the It's like, not to go too deep, but a particle detector is just, at least for dark matter, it's just a tub of liquid. And it's a tub of cryogenic liquid, so it's very cold. And it's put 2 miles underground, and it's under a shield, and it's all very, like particular, but it's just a tub of liquid. And that tub of liquid has a lot of atoms in it, and those atoms happen to be, in this case, xenon. And you choose xenon because it doesn't interact with other things. It's a noble gas. So just like helium or neon or argon, it doesn't really interact. It doesn't form molecules. It doesn't really have like a chemical decay to it, nothing like that. But it's really big. And scientists surmise that dark matter particles like really big particles, essentially. So you find the biggest non-reactive particle that you can, you put it into a tub. And then that tub is just sitting there with tons of atoms. And it's just waiting for a dark matter particle to hit it. It's just sitting there, that its sole purpose in life is to get hit by a dark matter particle, and almost none of them have a dark matter particle hit it. But that's what's happening. And those signals, that atom that got hit, as soon as it gets hit, it flies through the other xenon atoms that are sitting around in this liquid, and it creates a puff of light, basically. And stirs up some photons, essentially, and it's like 10 photons. It's a very small number, but you have these detectors that can detect the single photons, and those single photons are bouncing around inside your detector, and they're finally getting picked up by these single pixels, essentially, and you need to figure out, like, where was that event, right? And so you're talking about, like, really low statistics, pattern matching, and how do you make some kind of algorithm that says, hey, this is what the pattern that I got, where do I think this event was? And that was really successful in compared to what a human can come up with, essentially. And the other is determining the energy of the particle, how big of a splash was it? That's a little easier to do, but machine learning made it a little bit better.
And what about boosted decision trees lent themselves to application for this problem domain?
Yeah, so boosted decision trees, one thing is that they're like fast to train. So that was really good. They also, when you have a low number of statistics, or at least a fairly low number of statistics, they can still do pretty well compared to like a neural network that would overtrain or something. So we were very hot at the time on doing boosted decision trees for that type of problem, and I still think it's actually very good. And people are still using this, So yeah, it lent itself very well to doing that, the reconstruction, and it also lent itself really well to doing a determination of whether it is a signal or background. Was it a dark matter particle or not? Because because the signal that you see in this photomultiplier tube in the waveform, it actually does look different. It's like a little bit noisier, and it's a little fatter and things like that, but it's only kind of statistically noisier and statistically fatter, And so these machine learning algorithms can do a better job than our just standard hard cuts. A human can still do better than the machine learning algorithm. You can look at all of these, but you don't want to look at billions of events.
Interesting. Do you have a sense that there are maybe more that people with a physics background are somehow disproportionately represented in the machine learning and AI community? I'm only working on a small data set here, sample size, but I recently interviewed Josh Bloom, who is an astrophysicist and did an AI startup. Have you seen that at all?
Yeah, I do think so. And I run into a lot of people that have a physics background, and I think the reason that these two fields are kind of coming together is that AI is kind of just information physics. The way you try to solve a problem is exactly the same as how you would solve a particle physics problem. Like, get a ton of data, try to figure out what the trends are, try to see what the outliers are. Like, how do you actually tackle a problem? It's identical. I feel like I'm doing the exact same thing as physics, but I'm just doing it with voice now.
Super interesting. So before we get too far from it, you mentioned a lot of your work happening in China, and that there were some stories there. How did that happen? What's the connection? Yeah,
there was just an upstart experiment as I was starting graduate school. this experiment was just sort of being circulated as a possibility. There wasn't really anything going on yet. But people were like, hey, there's a spot underground in Western China. It's 2 miles underground. It would be the deepest lab in the world, and it's not a lab yet, but we're trying to petition the Chinese government to turn it into a lab so that we can put a dark matter experiment there. And I was like, I am so in, this, whatever that is that you just said, let's do it. And that's actually what it was. I went to my advisor, my new advisor at the time. I was like, let's do it. He's like, this isn't really a thing yet. And I'm like, I don't care. Let's do this. Right. And it eventually turned into a thing. It involved, China's an interesting place. So I'll say that. But at first, there were failed talks to turn this into a lab, and they went something like this. To back up just a second, like, why was this lab there anyway, or why was this spot there? They were building the world's tallest hydroelectric dam right next to it, and they have all these tunneling machines, and these mountains are made out of marble, and marble's really easy to tunnel through, so they like Swiss cheese the mountain. They just cut a whole bunch of holes in the mountain, and there just happened to be a tunnel that is 2 miles underground, and this is where they were diverting water through. So it's actually a new type of hydroelectric dam where they have a really tall dam part, and then they extract energy there, and then they go where there is a river that would go around a mountain, like a long distance around a mountain. Instead, they just tunnel through the mountain, and so the mountain itself is now a secondary dam, essentially.
Oh, wow.
Yeah, you can look this up. It's the Jinping 1 and Jinping 2 dam in China, and it was just completed like a year or two ago. But yeah, that's what they were doing, and so we were like, hey, this is a great spot to do it, and we went there and said, hello, hydroelectric dam company, we're like 10 scientists, and we'd love to put an experiment down here, and they were like, no. And so we were like, how can we work this a little better? And we were in cahoots with Shanghai Jiaotong University, which is a very well-known technical university in China. And we went to them, and we were in collaboration with them. And so, like, along with them and the leadership there, they said, oh, okay, we'll talk to some people, essentially. And so the educational system in China has a ton of power, and so they went to the leaders of the education community went to the hydroelectric dam company and said, hey, do you guys want to do this? And they said, sure. So they have some sway there.
It always helps to have the right people involved.
Yeah, absolutely. And so that's how that all got started. And from that yes moment to having a lab to actually work in, it was less than 9 months. They had to, get dynamite, blast out a lab, like turn it into an actual thing with cranes and like yellow railing so it looks like a James Bond lair. They had to do all of that, and they did it in less than 9 months, and we were in there building our experiment right after that.
And were you physically in China in this lab, or virtually connected to it from Michigan?
So I would physically go there like 4 months out of the year, essentially.
Okay.
Yep. And that was, again, like for me, I grew up in a really small town in Michigan, and I kind of figured out that like the world exists, outside of like a 3,800 person city, or city, I shouldn't say city, tiny town. And I went to, undergrad in Missouri at University of Missouri, St. Louis, and then I went to graduate school at University of Michigan, and the world is just getting bigger to me, and then now I'm like in China, halfway across the world, totally different people, totally different culture, and I was loving every minute of it. I thought it was great. And
that's awesome.
Yeah, and there was so much to learn from being over there, but one of the biggest is that they have very few roadblocks. Essentially, if you want to get something done and you have the resources to do it, you will get it done very quickly. And so that's why we could start the experiment. That's why they could build a lab in 9 months. That's why they could build this dam in 5 years. That's why we could start our experiment, like design the experiment, build the experiment, put it in, run it, etc., do all of our data analysis all in under 4 years, because they were just like so helpful in removing roadblocks. So that was really nice to see coming from the US.
That's awesome. So you worked on this project, finished your PhD, connected with your co-founder was also from Michigan. So you guys knew each other before.
Yeah, we were working on that experiment together. He's a decade younger than me, so essentially he came into University of Michigan at like 15 or 16 years old, and I was, like an old jaded graduate student, at that point, and started working in our lab, and he is just very good, and we hit it off, and would spend a lot of time together outside of physics too, like mining Bitcoin or building drones or whatever, just kind of having fun and doing technical stuff together. And yeah.
And so you guys started this company. You talked about how the problems were similar, but what was the genesis for the idea behind what you're doing at DeepGraham?
Yeah, so Noah definitely has to take credit for this, my co-founder. So I was a little naysayer at first, where he wanted to start recording his life. So he built a little device out of like an Intel Edison or a Raspberry Pi, one of these, that it just had a battery, Wi-Fi antenna, microphone, and a processor on it essentially. And he set it up so that it would record 24/7, and basically every minute make a new audio file and just sort of dump it into storage, and then whenever it came in contact with Wi-Fi, it would upload all of it. So essentially, he was backing up his audio life at least. And I was like, "What are you going to do with all of that? Trust me, your life's not that interesting. In real time." You're not going to go back and listen to it again, right? And he's like, yeah, whatever, right? And so he recorded like 2 weeks of his life, several hundred hours. And, you're sitting there at the end of it thinking like, oh, yeah, okay, now this is a real problem. How are we going to go back and find anything that we want to hear? And so we did the first thing that you would think of. Hey, let's turn this into text, speech to text. And when that didn't work very well, because that's just like the state of speech to text, essentially, where if you have a microphone that is not super high quality and it's not right up in somebody's face and the person is not enunciating really well, then you're going to get pretty bad word error rate, meaning, it's not going to be that accurate.
Right.
And so that's a situation for like almost all of the world's audio. It's not great audio, but in this case, all of the audio was like that. And we were like, okay, this speech to text thing is not going to work. Can we do something better? Maybe somebody in the world out there like Google, hey, they know how to do search. They know how to do audio. Maybe they've made some kind of API or something that can do this audio search, right? And so we started playing around and looking there, and we just couldn't find anything. And we found papers from like 2008, 2009, where Google wrote about this type of thing, like doing search in audio. Their technique was to turn it into text and then tried to search in it. And it worked pretty well when it was on a reduced domain. So they did like political speeches. And yeah, and they had fairly good results, but when you try to generalize it, it doesn't work very well because everybody speaks a little bit differently, and political speeches are well recorded, and everybody's enunciating, so it goes pretty well then. But if you try to do this in a general sense, it doesn't work that well. And we emailed or set up a Skype call with one of the engineers on the paper and said like, what are you guys doing now? Because some years had passed. Surely you guys are working on this problem, right? And they're like, no, we gave up on that. We're not doing that. We're just trying to make our speech to text better.
Okay.
And we're like, okay, so it's still not very good. That doesn't help us. So we started just working on it ourselves. We were like, okay, we know signals, we know machine learning, we know how to deal with lots and lots of data, and let's see if we can make some kind of search engine for audio. And over the course of about 4 or 5 months, we went from, very poor accuracy, meaning like maybe 20% of the time you'll find what you're looking for, to 80 or 90% of the time finding what you're looking for. So that's like going, state of the art's 20%, you're at 90%, you're feeling pretty good. So that's the genesis of DeepGraham, essentially. We're like, whoa, this has a lot of applications. And at the time, we were coming out of academia. We're like, hey, students can use this for lectures and whatever. But when we started to think about it a lot more, we're like, you know what? The world, like the big audio source in the world, the huge data lake of audio in the world, is like recorded business calls. So like customer service calls and things like that, just call center stuff. And they're all really low quality and nobody knows what to do with them, essentially. And we're like, man, like DeepGraham could be a massive company if we do this right. Yeah.
Well, I think the other killer use case is, I don't know if you're married or not, but my wife and I always have this conversation where, oh, I just told you this, or no, you didn't say that, or whatever. If I had his device and recorded all of our audio and then could easily go back and prove whether I said that or not, there's got to be a huge market for that.
I love this use case for DeepGraham because, yes, I feel the same way. Actually, we've run across a lot of people, though, that are like, oh, no, this will make things worse.
It probably would, because I probably think I'm right more than I actually am, much more than I actually am.
Yeah, exactly. But no, I think there's a regularizing effect there, that if you know that there's something recording, maybe before you say, I know I said this, you'll actually go back and check or something, so I think it could work out. And actually we do kind of think about this problem. I think the market's not really ready for it yet. If you just put a recorder on everybody and said, now we're backing up everybody's life and everything you say is recorded, I don't think people right now are going to be super into that. But it might come. And I kind of hope it does. Like for me, I wish I had it. And we do have these devices like laying around our office from those days, where I think, man, if I was just wearing that all day, every day, then that would be great. Of course, they're very heavy, so we don't do that now. But you could make it much smaller. And
they're probably a lot lighter than they were then.
Yep.
Interesting. So you described the frustration that you were having with trying to do this, and the state of the art being turning the audio into text and then running a search engine against that text. Is the implication then that you guys are not using text as an intermediary?
Yes, that is true. So we do build an index just like you would. So, this is sort of the terminology that you would say before you built an index out of text, right? Well, we're not building an index out of text anymore. We're building an index, like actually out of activations in a deep neural network, so activations in a representation that's deep in a deep neural network. The best way to think of that, though, is that you're doing something kind of like searching through phonemes. So phonemes are like the alphabet of speech, right? But they're kind of a human. They're like humans have assigned those. Like these are the 40 phonemes, or these are the 53 phonemes. Like you don't have to do that. You can just have it be defined by the data, and so that's what we do. But if you look at what these match up to, it's very similar to phonemes.
So that statement that you quickly went by kind of blew my mind a little bit. You're building an index out of activations deep in a neural network. Elaborate on that a little bit for us.
Yeah, absolutely. So the output of a neural network is again just an activation, essentially. And what you're doing is you're forcing it to, like, in the case of a speech recognition, you're forcing it to guess, like, what is the word being said at this time. Sure. Or in the case of, like, doing some multi-class network that's trying to guess, is this a handwritten 0 or handwritten 2 or something like that?
Right.
Then it's trying to guess
decision.
that. Yeah. And so if you just sort of back up one layer from that, it's still pretty close to that output. It's just some like linear combination that has been stuck through an activation to get to that output. And so you can think of images where at the very top, or it depends on how you think of neural networks, but near the input of the neural network, it's looking for edges or round things or something like that, right? And then as you get deeper, it's looking more for like faces or trees or something like that, right? And the same thing is happening in audio, and now it's looking for things that are kind of word-like or kind of like portions of a word-like, right? And so those activations are what we're interested in.
And how deep are the networks that you're typically using, and how do you know which of those activations to tap into or capture? And is that static or dynamic? Does that change based on the utterances, or how do you figure all that out?
Very, very great question. so there's several ways to go about this problem. You can just say literally let the data define this and go to town. That does work pretty well. You can sort of get a boost in accuracy, a little bit of a boost in accuracy if you pin it at first. Like when you're training, you might pin it to phonemes, or you might pin it to some larger subset, and then remove that restriction. So it's sort of seeded that it should have learned something like this, and then now it sort of builds off that knowledge. So that's kind of how you can guide the network. You're pointing it in a direction that's approximately correct, but then you relax that and allow it to pick the things that are working best. The things that we're working on right now to make this even more accurate are, instead of a word target, you are searching for not searching. You're trying to force the network to guess like a topic or a part of speech. Is it a noun or a verb or something like that? And you do all of these things at the same time. So your network is sort of branched out, and it knows, I'm trying to guess words. Fine. I'm trying to guess a topic. I'm trying to guess all of these things. And so when you force that restriction on the network, then you can control kind of what the activations are the information that the activations are holding. You can kind of control that by the target.
So how can you say how deep your networks typically are? Are they what you would think of as, very deep, tens, hundreds, or more layers, or are they relatively shallow?
Yeah, we're in the tens, in the tens category. And we have had a lot of success in that regime. If you go deeper, you need a lot more firepower on the computational side.
Sure.
And you need more engineering on the, like, where do I put my skips and where do I put everything like that.
Right. Architecture becomes more complex.
Yeah, exactly. And so we're we're like an 8-person team, so we don't. We try to minimize some of those engineering bottlenecks as much as possible, and we've seen very good. Well, I guess another way to say this is that if the state of the art's 20% and you're like in the 80 and 90% range with the networks that you have, then like you could spend a lot of time turning it into like 92% accurate by making your network a lot deeper or something like that. But
right.
We don't focus too much on that yet until we have the pressure to do that.
Okay. And so with the network in the tens of layers, then it sounds like you have a pretty good sense based on your architecture of where, what layer is the phoneme layer versus, I don't even know names for the other.
We don't know names either. Honestly, like this it would be really this hasn't been explored as much as images. There are sort of reasons for that, like where are the data sets to do this? Also humans, I think, are not as interested, or I guess it's harder to ingest audio than it is images. Images, you like instantly see it. You're also entertained by the images that you see, but the if you hear audio that you're not super interested in, you're like your eyes glaze over right away, right? And so labeling the audio data is expensive and time consuming, and you can't just like click through a bunch of things and now you've labeled a ton of images. You can't just click through a bunch of things and label a bunch of audio files. Like that just doesn't work. And so those are kind of the problems that audio faces, but also you can't point to things and you can't point to things and say like that little edge feature right there is important because you're hearing it, right? It's just not. We don't have that visualization capability, and so it's a little more challenging in that regard. So yeah, we don't have names for this stuff either. There are linguists out there in the world that probably have some names, but we just look at like a 2D FFT, a spectrogram of the audio and say like, ooh, I can sort of see what's going on there. And you just kind of treat it like it's an image and think of it that way.
Okay. So the other interesting use case that occurred to me when I first saw your stuff was, I've got a bunch of audio in the form of podcast interviews, and I'd love to find a way to make that more accessible. And one idea that I've had for a while is, hey, it would be great if I had a bot, like a Facebook Messenger bot or a chat bot or whatever, where you pull this thing up and and you can ask it, hey, I want to find TWIML episodes about convolutional neural nets, and it will look in its index and tell you, oh, check out episodes 13 and 5 at times X, Y, and Z. It sounds like you're saying that your stuff could be a part of building that. So what would the process be to get to what I'm talking about? Forget all the bot stuff, but just in terms of the voice search engine piece.
Yeah, that's exactly right. The mentions is a part of it, and topics is another part of it. And that's exactly the type of problem that DeepGraham solves. So you have a lot of audio, right? And you have listeners that don't want to sit through 20 hours of audio trying to look for that one little tidbit of information that they're interested in that time. And that is what DeepGraham solves, and that is actually kind of a really interesting interactive experience once you finally do it, So like when we first built DeepGraham and we made, the search engine, and it actually found moments where we were like, whoa, this is exactly what I was looking for. It's a totally different experience than what you would feel if you had tried to do this with speech to text. And so yeah, we're very into solving that type of problem. And the way that you do it with DeepGraham is we provide an API. So you go and sign up at deepgram.com and create an account, and there you upload your audio and you give us the query that you're looking for. So if you're looking for convolutional neural nets or CNNs or convolution, you put those keywords in, send it to the API, and you'll get the results back of all of the mentions that were in your audio. And if you want to make that go even deeper to it's where it's more topic based rather than keyword based, then you sort of work with us for a custom API endpoint to build a model that is more tuned to the topics that you care about.
And that is essentially you guys working in a professional services or whatever capacity to build some I don't know, what does that process look like from your perspective? What are you actually doing behind the scenes to make the topical stuff work?
Yeah, good question. So the general stuff kind of works right off the bat. Hey, you want to search for a keyword. We have a lot of data that we've already trained on, and even if your keyword isn't in there, we can find it because it's essentially a fuzzy search. But if you want to do this topic modeling, then what you do is give us labeled data. And so in your case, it would be I have all these episodes, and they were the contents of these episodes. You would have to know this. We talked about convolutional neural networks in this one. We talked about recurrent neural networks in this one, and boosted decision trees in this, and we talked about productizing in this one. And you just put those simple labels in, and then you train a model, and it doesn't have to be a deep neural network either. At that point, because you have such a small amount of data, you probably do something like a boosted decision tree. But you train this model to do that topic prediction based on the search in your audio. And this is actually getting really into the weeds, but the way that it actually works is we utilize the search for that topic modeling. So our search is the best in the world. It's the most accurate. And if you train a model with a target that says, here are these topics, and I want you to be able to predict these topics, and I want you to be able to generalize to other audio files, then our model that we're building, whatever it is, but that topic modeling model, it is going through, and it's not doing any heuristics whatsoever. It's sort of exhaustively searching all the possible phrases and saying which ones help and which ones don't. And it's recursively eliminating the ones that don't help, and it's arriving on things to search for that are very good. And it doesn't have to be a single search term. It could be 10 search terms. And it also might be the non-existence of a term. It's if you're talking about these 10 things and this other one, then it's some other topic, and et cetera. And I don't even know how it works, right? That's how it works. And then in the end, you look at the output and you say, like, these are the things it's saying search for, and these are the things it's saying don't search for. You don't want these to exist, and that's how the model works, and it works extremely well. So yeah, that's sort of how the sausage is made.
And how much data do you need in order for you to start getting interesting results, both from the basic search and the topic modeling? Or is the fact that you guys have already trained your model, let's start with that question. Is the fact that you guys have already trained the model on the data that you already have, does that mean that I don't need to have some specific level of data about my domain in order to get good results?
Yeah, in some cases that's how it works, where, if you have sort of like a broad topic, like, is this about sports or is this about politics, then that data is sort of already lying around and incorporated into a model. But if you're talking about niche markets, then you probably want to supply something, and then we'll, build a model on top of that. But that the data that you supply probably isn't the only training data that we're using. We're just supplying that. It's essentially a form of transfer learning, and then we're like changing the target of the model.
Mm-hmm. And so what am I supplying then?
Yeah, you would supply like audio with some tags. So like, here's an hour-long audio, and here are the 20 things we talked about, or here are the 10 questions I asked, or something like that. Okay,
and the neural net can just figure out what's relevant and what is, and kind of map those to the tags.
Exactly.
Even given, I would imagine a fairly limited, or how much audio and tags do I need to give the model for that to be useful?
For it to be useful to a consumer that's searching for something, because they're fairly error tolerant, actually, right? Like, if you get 1 out of 2 wrong, that's not too bad, as long as one of those is okay, right? As long as one of those is what you're actually looking for. So you probably need something like 50 or 100 different labeled files, and you'll get results that are similar to that. If you have around 1,000 labeled files, then you get results that are more like 90% accuracy.
And these are hour-long files or shorter?
It kind of depends on what you're searching for, but they're generally in like the 10 to hour-long range. You'll need more files if it's only like a minute long.
Okay.
Yeah.
Oh, interesting. And so then what you guys are offering is a service, and that exposes an API, but you also have done some work around an open source framework. Let's talk about that for a little bit. So why don't you walk us through what you've done there?
Yeah, we're extremely pumped about it. It's called Kur. It's open source. You can go contribute to it. It's on GitHub. But the idea behind Kur is that years ago, around a decade ago, GPUs came onto the scene for neural networks. Data started to become available, and it became a really smart idea to start training neural networks on GPUs. And the people doing it back in the day knew something about GPUs. In order to accomplish that task, you had to have some like domain expertise in order to pull it off in a good way. And NVIDIA started to pick up on this and said, hey, we're going to make CUDA, a framework that allows like C developers to get a little handle into the GPU and be able to train things that way, or be able to use the GPU for matrix multiplication and things like that. And so that's like another layer. You have the bare hardware, and then you have like CUDA, and then you have Brian Catanzaro making cuDNN so that it even works better for deep neural networks, right? But this is still all very low-level type stuff. And then, out come other frameworks like Theano or Caffe or TensorFlow. And those are another abstract layer on top. They make it more human palatable, right? And
right.
They're much more palatable for the developer or computer scientist that, really knows their stuff, right? And that's totally fine, and they work very well. What we have found out, though, working internally at DeepGraham, is that working in those frameworks still is very slow for us to try to do experiments, essentially, to try new model architectures and then see the result, because we're not necessarily training time limited. We would really love to be training time limited. We are engineering limited, and so it's like the time that you're putting in to sort of cook all of this up and do all of the error checking and whatnot to make sure it's like training the way it's supposed to. We're like, man, why don't we just make some other framework on top? Let's just stack another framework on top that is more abstract, that sort of doesn't care about the back end, and it doesn't care, if you're using Theano or TensorFlow or whatever. You can just switch it with a flip of a switch, and if something's faster, fine, whatever. But like, all we really want to do is describe our model. We want to say, hey, the input is going to be this audio. Then we're going to have a 2D convolution, and another 2D convolution with a batch norm, and then we're going to have a few recurrent layers. Those are going to have batch norm too, and then we're going to stick those out into a dense that then predicts at every time slice which character is going to be there, or which word is going to be there. And so that's how we want to think of it. We don't want to think about like Python code and like how do we like put all of that in there. And so that's what we started working on at DeepGraham, is like, how do we do that so that we can multiply our engineering effort, essentially? I just go in and I change a few settings and then start running my network again, and then go off and do something else. And that's exactly what Kur is. It's a descriptive deep learning framework. And, we have examples on how to do image classification, examples on how to do speech recognition, with a network that's very similar to Baidu's deep speech model, and language modeling and things like that. And it's all in this descriptive format. It's still not like, don't get me wrong, like deep learning is still not easy because because there's a computational problem there and there's a data problem there. Like, how do you get it into the format that you need? How do you collect the data? How do you clean it? Everything like that. But the model part, once you have your data and once you're all set up, the model part is now like so much easier for us using Kur. And so we thought, this is kind of a competitive advantage. Yeah, it is. But we have gained so much knowledge by using open source software and talking with people very freely sort of in the deep learning community that, this tool has been so valuable to us. Let's just release it. Like, we're probably going to get more, than if we just kept it to ourselves, and we actually have. Like, we released the Kur framework, and within like weeks, somebody had added multi-GPU support, and I was like, whoa.
Oh, wow.
These people are serious, right? And So yeah, and this is also another way to like, if you're an AI company out there in the world and you want to hire engineers, this is another way to find good ones, and they could be across the world. And so it's like we want to be giving to the community. We also just want to be part of that conversation, because I think we have a lot to add, essentially. And I think that the deep learning community, there's so much demand to there's so much hype, first of all, but there's a ton of demand for talent, and there's a ton of demand for the type of critical thinking you need in order to solve these deep learning problems. You don't have to be secretive. You don't have to be like, this is our secret sauce, whatever. No, everybody is like talent limited, they're computationally limited, they're data limited. They're not like good idea limited. So
right.
So yeah.
You mentioned it's declarative. That's one of the main things it's doing. Have you created like a DSL to define your neural net, or is it a different type of expressed differently?
Yeah. Okay. Great. Yeah. Great question. And the way that you interact with Kur is you pip install it, and so it's written in Python, and you can use it as an API just as you would Keras or something like that, where you're programming in Python, and that's just how you use Kur, and that's totally fine. Okay. But sort of the DNA of your model is contained in what we call a Kur file, and that is YAML or a JSON. And so that contains like your hyperparameters, your model architecture, like how you want your data to be supplied and things like that. And a lot of that is boilerplate that is already out there in examples, essentially. And so you just like use a Kur file that somebody else has put out there in the world, and then just edit it a little bit for your purpose, essentially. And so, yeah, that's how it operates. Just basically YAML files. And if you want to do like a deeper surgery, then you do it in Python using the API.
And does it does it sit on top of any of the other frameworks, or how do you leverage the work that's being done on TensorFlow and all the other frameworks out there?
Yeah, absolutely. I should have said that earlier. It does. It supports Theano, it supports TensorFlow, and it supports PyTorch. And maybe we'll support other backends since like Deep Learning 4J is working its way into Keras now. We'll probably be supporting them soon. So yeah, that's kind of how it goes. If you have a high level API that would fit into something like Keras, then it'll fit into Kur as well.
Okay.
Yeah, but we've already done the legwork for those three, TensorFlow, Theano, and PyTorch.
Awesome. And you mentioned this already, but it's not just for audio; it's for images and basically anything that you're trying to use a deep neural net with.
Absolutely. All that we do at DeepGraham is audio. That's true. But the Kur, and the networks that you can train using Kur are agnostic. It doesn't matter. You can do sequences, you can do audio, you can do, text, audio, images, cook it up and you'll be able to do it. We just had a hackathon last weekend, and people were doing all sorts of things, music, editing videos on the fly so that your cat will look like a Van Gogh as it's crawling around and things like that. They're using Kur to do these things. So yeah, it's sort of agnostic.
That's very cool. Very cool. And so you mentioned the Baidu Deep Speech stuff. Was that the inspiration for Kur, or to what extent is the DeepGraham work, your product based on that research?
Sure. So the models that we use to build our indexes and to ingest audio are extremely similar to the deep speech networks. You have a convolutional stack and you have a recurrent stack, and the target is characters or words. In the deep speech case, it's characters, but nevertheless, the architecture is extremely similar. And so the networks that we supply, like in Kur, the examples that we supply in Kur are extremely similar to what we use. But we have tried to make networks that people are already familiar with, like they can go read a paper and figure out how it works, right?
Okay.
And we put that into the example file as well, saying like, hey, if you want to read about the architecture, this is where it came from. So that's we're not trying to confuse anybody about like how it works. So we sort of stick to the things that you can go out and look at a paper for. DeepGraham has not written a paper on what we're doing yet. It's kind of in the works always, but we really would love to. But when you have like businesses to take care of, and customers, I guess, to take care of, and only 8 people, then that kind of gets thrown by the wayside.
Right. Are there any standout use cases for this approach in DeepGraham? Anything that you're seeing as kind of coming to the fore in terms of what people want to do with it?
Absolutely. From the business side, there's fraud detection is a really big one, where people will call into financial services companies and try to get money from them, essentially try to take money out of your account, or get a credit card sent to the wrong address or something like that so that they can take advantage of it. And there are sort of patterns in this, and these companies have hundreds of millions of calls every year, and they're trying to correlate these things and say like, hey, we know that fraud happened on these calls, etc. Can you like help us find where that's happening? Like every day people are calling in trying to defraud us. Can you at least give us an alert so that we can look at those harder? And that's just that's one of the channels that provides a lot of value essentially to the world. Because if there's lower fraud, then everything becomes less expensive for everyone essentially.
Right.
But there's also like a quality assurance aspect to this and compliance aspect. Again, this is still in calls where, are people just saying the things they're supposed to say? Are they having good responses? Do customers have nice interactions? And having the way that companies deal with this now is they pay humans to look at maybe anywhere from 1% to 5% of the calls, and generally this is outsourced where you send them a random selection of your calls, and then you say, like, tell us what happened in these calls, and they'll report back with a rubric of maybe like 10 or 20 different things, and the quality will be pretty low. Mm-hmm. And that's like the only source of truth for these companies about their customer interactions that happen through phone calls. And so that's the type of thing that, DeepGraham is trying to help with. We take like that QA data that you've sent out to have humans label. We'll help you figure out which of those labels are actually good. And then we'll build a model based on those labels to predict all of your audio, essentially, to predict the contents of all of your audio. And then you can take your QA team or your compliance team or whatever they're doing, you still have hundreds of these people like listening to all these calls. You point them in a new direction, so they aren't doing the same like rote thing over and over. They're like actually using their brain to do things that humans are really good at, which are like creative things, like figure out, a new way to find fraud rather than just sort of listening and hoping that they detect it randomly, So this is like where DeepGraham has a huge impact, I think, or has the ability to have a huge impact, is just automating that entire process. So for the consumer side, we're not putting as much effort into making a product like Google for the internet, but for audio.
Right.
I wish we were. Like, actually, this is a product, and somebody should build it using DeepGraham. But and we have built demos of this where you just scrape a lot of YouTube videos, and then you're able to search it using DeepGraham's tech. But I think from a like company health perspective, like in other words, DeepGraham not dying in 2 years and not having to raise like $200 million in the process of that death, it could go a lot of ways. But essentially, I think that product is like available, and it's something to test. I think that just the greater human world right now is not necessarily ready for it at this moment. But in the next couple of years, that's what we're going to expect. We're going to expect that all of the content in the world is searchable. That when I think of like a movie quote, or when I think of something that I listened to in a podcast, or when I think of some interview that I saw on YouTube, and I think like, oh yeah, they talked about this and they talked about that, I should be able to search for it and I should be able to find it. And people will start demanding that soon. But yeah, we haven't spent. We did some market research on this, to figure out is this an area that we should spend our effort right now? But it just isn't yet. Maybe we'll start doing that, in the next couple of years. But it's not our focus yet.
Awesome. Well, this has been a great conversation. We talked about Kur, and that's open source, and we'll put a link to the GitHub in the show notes. Anything else folks should know to look for, or how to get in touch?
Yeah, you can get in touch with DeepGraham on Twitter at DeepGraham AI, or you could send a message to me at scott@deepgraham.com. I am not shy about throwing my email out there, so if you want to contact me, just go ahead.
Awesome. Well, thanks so much, Scott. It's been great having you on the show.
Sam, I appreciate it. Thanks.
All right, everyone, that's our show for today. During this interview, you may have heard me mention my previous interview with Josh Bloom, whose company Wise.io was acquired by GE to help them permeate machine learning and AI throughout that company. If you haven't already listened to that show, which was number 5, you should, because it was a great one. But even better, you should plan to attend the Future of Data Summit, because Josh will be speaking there on building AI products and running them in production. Really, you don't want to miss the summit, so check it out at twimlai.com. And if you work on machine learning and AI for your company, and you think you've got an interesting story to share, don't hesitate to reach out. I'm finalizing the agenda for the summit soon, but I'm always looking for interesting user stories. This podcast is full of great quotes. Don't forget to share your favorites, for one of our TWIML stickers. You can share them via the show notes page, via Twitter, and via our Facebook page. The notes for this show will be up on twimlai.com/talk/19, where you'll find links to Scott and the various resources mentioned in the show. Thanks so much for listening, and catch you next time.